Good day, everyone. How are you guys today? All right, thumbs up, good to see. Today, we'll go over a little more general information and then some foundational things about physics itself, and then some unit conversion stuff, and then we'll probably leave off there for the weekend. I want to talk a little bit more about WebAssign first, because I've been getting some emails about how to get into it, which is completely fair and exactly what I expected. Before we get started today, does anyone have any questions about anything? Yes?
Which access plan should we get?
That depends entirely on how much physics you think you are going to take. If you are only going to take this class, then you only need one semester. If you know for a fact you are going to take Physics 1510 in the spring, the next physics class, then you go ahead and get the extended version. If you're not sure whether you're going to take Physics 1510 at all, or if it's going to be spring or not, I'd recommend just getting the one if you don't know for certain. Just to err on the side of caution. But if you know for a fact Physics 1510 is going to be what you take in the spring, I'd go ahead and get the gear. Does that answer the question?
There's like two different options, and like one's like $100 and then like one's $119, but it's not like a semester thing. I think it's like it gives you different access to different like sites.
Okay, in that case, you only need WebAssign specifically.
Okay.
So if there's like another service they're trying to hawk on you, WebAssign's the only thing you need. Didn't realize that. A lot of these issues stem from the fact that I, as an instructor, don't really see the end of WebAssign from the student's view very frequently. So a lot of issues come up on the student side that I've never seen before on my end of it. So I want to make sure to help everyone with those as they come up. While we're on the topic of WebAssign, some people have asked for some help actually getting to the correct pages on the site itself. To get to this page, I just typed in webassign.com. Because there is some confusion. WebAssign is owned by a company called Cengage, and they have a bunch of things that they try to sell to students who don't know any better, and teachers who don't know any better sometimes. And if you go to the Cengage site, it's kind of a rabbit hole to get where you want. So I generally recommend going straight to the WebAssign site. And on this site, there's the gray enter class key button. If you just start from there and just go enter class key, you will be asked for that key, and that code is here in the syllabus. So presby.sc space 1232 space 2069. Putting that code into that spot, which I try to do now, if this PDF would let me. Welcome to Cengage. So you will see name of the class, my name. This is what the book looks like, and it's there to prove that the math questions we're using come out of this book. So again, you don't need it physically if you don't think you will ever use it. It is a good resource though if you like books. Press continue. And since on this page I have not been signed in on my account, this is a different browser than the one I usually use, you are prompted to either sign in or create your account here. So if you have a WebAssign account already, if you've already made one, then you sign in at this point. If you haven't, you can create your account, and it should ask you at some point for your access code. But if you don't have a code yet, say you bought one through a bookstore, either with a book or without a book, and for some reason the bookstore is deciding to take its sweet time to to send you a string of numbers, which I find infuriating. They stock them like physical books, and I don't like that. Then WebAssign does have I believe, 1 month free access period, so that if you are still waiting on a code to show up, because ironically the period in which everyone needs the books is when bookstores get the slowest, then you will be allowed that 1 month of time to just be in the class before the actual thing shows up. So everyone should be able to get in and view things even if you don't necessarily have that code yet. I generally recommend buying the code straight through this page. You'll create your account, it'll prompt you for it. I tend to advise people to get it through this site rather than ordering it by a bookstore, unless you want the book as well. But because you can create the account and get the free access period, everyone should be able to get in to be able to start working on things. I am planning on putting the first homework and the first quiz up in the near future. They are not going to be due in the immediate future, so that there is no pressure for you to get on and do something and finish something over the weekend. I don't want that for you guys. I will be putting up an assignment largely so that I don't forget to, because if you've been in science very long, you probably know most scientists are all absent-minded and eccentric. I'm no exception. I will forget things frequently, and I apologize in advance. So I'm probably going to go ahead and put the homework up because it's already in my brain and I don't want it to leave my brain. It will not be due until about here-ish, I'm thinking. That gives us a whole week of learning, and then I don't like making homework due like on the weekend. I've had instructors made homework due like, midnight Sunday, which gives you the weekend to work, but it doesn't give you a chance to come ask questions after you've done all of that working. So I tend to make the homework due either on Monday, so we can, like Monday at midnight, so that we can spend Monday looking at things and answering your questions. Occasionally Wednesday at midnight if I feel the need to push it back. So the first assignment's going up, but it's not going to be due until probably Wednesday, September 8th at the earliest. It's just going up so that people can look at it as soon as they want to. For right now, your main objective is still making sure you can access the page, and then the homework will be mostly about things that we learn next week. So for right now, just gain access. Any other questions or difficulties encountered getting into WebAssign so far? Okay. Any general questions, comments, concerns, random things pop into your head, etc. before we continue today? Okay. I took down the clock because its battery is dead, but now that's just as distracting. Anyway, it's still the beginning of the class, so let's talk a little bit about what physics is and its foundations, and probably some basic unit conversion type stuff that's going to be important for the rest of your scientific career, and every teacher ever is going to spend at least one day reminding you of it. Sorry. So, I have already hinted at the fact that, or at least defined by a physicist, physics is the study of the universe around us, and in general we tend to study the world around us by making observations and then describing those observations and the data in terms of math. That math frequently takes the form of algebra and calculus. The legend goes that calculus was actually invented by Newton in order to do physics. which tells you exactly the type of person he was. And again, because you're hearing all of this from me, a physicist, it's going to, I lost my train of thought, and it'll take me a second to regain it. Pardon me for a moment. I am a physicist. I like physics a lot. I get paid to talk about it, which to me is a dream come true. Not to everybody. Some people don't want to even be paid to hear physics, and I understand that completely. Because I'm a physicist, and because I like physics, I want to actively attempt to keep my explanations as undisciplinarily biased as possible, because there's a lot of things any given person can study, and I tend to describe things in terms of the physics, or why it's important to physics, or this is really cool because physics explanation. And I want to try to make sure my explanations don't require you to be a physicist in order to understand them. Additionally, I want to go ahead and say physics is not perfect, because physics was invented by humans. Caveat, the universe was not invented by humans, obviously, but the way that humans have studied the universe was invented by humans. The definition of physics is not the immutable truths of the universe. The definition of physics is humans' study of the universe. Therefore, it is a human practice and a human art form, which means we invented it, and that means it's inherently flawed and imperfect. The universe is going to do what it will do, regardless of what we think is happening, because that's what it was set in motion to do. All of science is mankind's best attempt at trying to understand and predict why the universe does what it does. And very frequently, scientists are wrong. For as long as humans have been observing this, we've had opinions as to why it happens. We've taken data, we've tried to figure out why, come up with explanations, and for a lot of human history, we've been wrong. I want to go through kind of a classic chain of events that sort of shows how flawed science can be. If you go back thousands of years, let's say go back to the age of Greek philosophers, the people who were arguably the first physicists, because not only were they thinking about ethics, they were also thinking about the universe around them. At least one of them, I keep forgetting who, names like Plato and Aristotle and that group keep popping into my head. At least some of that generation of thinkers were under the impression that the world is made up of stuff, and this roughly became the concept that would become our understanding of atoms. That stuff was made up of earth, wind, fire, and water. Our understanding of the universe has developed significantly since then. Cut to about at least 1,000 years later, we had this guy. Very important figure within physics, arguably one of the most important classical physicists of all time. Not to discredit the work of others, but there's a reason that we study Newtonian mechanics first. It's foundational to our understanding of what happens on Earth. Isaac Newton developed a series of equations that solidified how mankind looked at the universe for hundreds of years. This is arguably the most famous of those equations, which I believe most of you should have seen by this point, or at least heard quoted to you: force equals mass times acceleration, also known as Newton's second law. And Newton's work became like the golden standard to all physicists. It worked so well and so often, all physicists and scientists who used physics for a long time thought that Newton's work was perfect. Newton's work is exactly how the universe works 100% of the time. There's no point in putting any research into refining his math. Which, considering the fact that he was just one European man, means that automatically that one assumption had to be wrong. Of course he made an error somewhere. As opposed to, the millions of other scientists that have existed throughout history. Now, this formula is really good. There's a reason we still use it. And we were able to use this to predict the motion of every planet in our solar system, except one. Any guesses on which one that was? There's only 9 of them, 8 of them. Pluto. It is not Pluto, but that is a good guess because it is the furthest one away. It's actually the opposite end of that spectrum, Mercury. Every planet we were able to predict using this formula and the similar gravity formula perfectly, except Mercury. Mercury was always slower than we thought it would be. And scientists loved this formula so much they didn't want to admit it was wrong. So instead, they did a bunch of other math and came up with the idea that there must be some other planet hidden behind the sun affecting Mercury's gravity in a way to create its unique orbit. They used Newton's equations and determined where that planet must be and what its mass must be for that to happen, and they just assumed it was true. They just assumed this planet existed because it would have to for this equation to work. Guess what they called it? For some reason, we still to this day insist on naming our solar system's planet after Roman figures, and Gene Roddenberry, who created Star Trek, borrowed this name. We called it Planet Vulcan. So you can look up actual astronomical models of this solar system that were made for about 100 years at least that had Planet Vulcan on them, because they figured, well, it has to exist. And when we finally invented a probe with a telescope on it that was able to go around the sun, guess what wasn't there? No Planet Vulcan, no Spock. So, this is wrong. At least in some situations, Newton's work just didn't work. Which probably crushed a lot of crushed the hearts and minds of like 3 physicists, probably. Enter this man, also very smart. Newton kind of set the stage for like classical, Renaissance era physics. Einstein helped redefine modern physics within the last 100 years. And his work into things like spatial relativity and the creation of this formula, which you should have all seen, helped us realize that Mercury isn't slowed down because there's another planet whose gravity is affecting it. Mercury is slowing down because the sun is bending space and time and making time mean a different thing at Mercury's location. You will never have to do any of that math in this class. I just think that's super cool. If you've ever seen Interstellar, you've probably heard something about that already. That whole chain of science and history just to say physics can get busted sometimes. It doesn't always work because we made it up. It's just our best guess at why things happen. And we can be wrong. And that's okay. But I am going to do my best to teach you our best guesses as to why things happen and to help you use that subconscious knowledge that you've observed your whole life. Lost my train of thought mid-sentence. That's probably a problem. Help you use that knowledge you already have to help you understand your own world a little bit better. So, physics is science. Science is imperfect because, again, humans invented it. But we have developed for ourselves a set of guidelines that we follow to try to keep things as scientific and objective as possible. You've definitely seen these steps before. Most science teachers probably begin their year reminding you about them. find no exception. And the steps of the scientific method are important, because if you don't follow them, you're not really doing science, and well, lost my train of thought mid-sentence again. I'm thirsty. I'm going to take a quick pause. How are you guys? Stay hydrated. If you want to do science, if you want to try to find as close to the objective truth as the human brain can actually arrive at, you need to follow these steps. And you can use these steps to study anything, really. Like, anything has the potential to be science. To quote one famous mythbuster, the only difference between science and messing around is writing things down. As long as you have an experiment and record your data, you are doing science. And that can be applied to functionally any discipline. Within academia, there tends to be this chart, not really a hierarchy, just a scale of whether your discipline is objective or subjective. Arguably, the most objective thing you can study is math, because the numbers don't lie, they're just confusing. Physics is applied math. We use math to explain the universe. Chemistry is applied physics. Biology is applied chemistry. Psychology is applied biology. Sociology is applied psychology. Then things get kind of fuzzy, and you eventually end up with art as the most subjective and least objective thing you can study. But that doesn't mean that there isn't still some scientific way you can examine art. It's just fuzzier. But you can do it as long as you follow these steps. So, again, just as review, in order to do science, you must first observe something happening and ask a question. Why did that happen? It's as simple as that. I would say step 0 is don't sleep under an apple tree, because you will inevitably get conked with an apple on your head. But if you do sleep under an apple tree and an apple hits your head, you've observed something happen, and then you ask why. Well, why is you slept under an apple tree, but why did it fall is a different question that we can still examine scientifically. Once you have your question, you want to do research to see if anyone else has already tried to answer that question, because you don't want to waste your grant money finding something that someone's already found. And frankly, people these days are very good at this step, because every time you've pulled out your phone to Google a random question that popped into your head, you were doing research. It's just a lot faster now, because the search engine does the actual searching for us, and we don't have to go combing through massive piles of heavy books. So, one benefit to living in this age. Once you've done your research, you determine whether or not there's already an answer to your question. If there isn't, then you need to think about why your question is, why things happen the way you observed them. You form your hypothesis. And the best definition for hypothesis is an idea. It's just your idea, your basic thought about an explanation, an answer to your question that you're asking. Any idea can be a hypothesis, and hypotheses aren't special. Anytime you've ever tried to explain something, that's a hypothesis. I don't know why we have bothered inventing a fancy Latin word for it. Latin, Greek, I'm not a linguist. Once you have your hypothesis, you're going to want to test it, perform experiments to collect data. The data is the only part of this whole chain of events that is empirical, measurable truth. The rest of it is human extrapolation. This is technically the only part you can actually count on for absolute certainty. But you want to do your experiment, collect your data. If your data supports your hypothesis, you collect more data anyway to double check. If your data doesn't support your hypothesis, you repeat steps 3 through 5 until you find a hypothesis that actually works. You have your data, you have your hypothesis, you keep testing it. If your hypothesis keeps working, if it keeps serving as an explanation, the data keeps supporting it, you need to publish it and share it with other scientists who will then perform their own experiments to see if their version of your hypothesis is correct or not, or at least if the data supports it or not. Sharing research is a lot faster these days. You used to just have to scream into the street and hope there was another scientist within earshot. Thankfully, now information spreads quickly, and as a result, new smartphones are made in a matter of months. Share your research, other scientists will test it. If after enough time, enough scientists find enough data in support of it, it becomes what is known as a theory, and if after hundreds of years, enough scientists find more data in support of it, and no one can argue against it, it becomes known as a law. What that means is, and I've probably made this point several times already, every law of physics technically started as a hypothesis of physics, which means it was just an idea that popped into some human's head. When I explain the laws of physics to you, I'm not necessarily describing the immutable truth of the universe. I am just describing to you our best guess as to why the universe does what it does. I don't think, as humans, we will ever really know exactly why everything happens this side of heaven, which is exactly why we need to stop arguing with each other and just figure out cold fusion. But if you follow these steps, you can really make anything into a science. Any questions? Okay. One more quick point before we take our mid-class pause. Even using the scientific method, there is a way to be more scientific about it. In physics, we try to perform what is called operational science, which is to say we have data for every single part of the experiment, and we know the state that our test subjects were in at the beginning, in the middle, and at the end. We have data for every part of the entire thing, and therefore we can use that data to conclude about every single step of the process. An operational experiment would be one where you have your test subject, you put it in place, and you ask yourself, what is going to happen to the test subject if I do X, Y, or Z to it? You are not performing an operational science if you don't know exactly what the state of your test subject was at the beginning of the thought experiment. For example, I could ask you how many markers are currently on my desk, and you could come count them, but you couldn't necessarily tell me if there was always that many markers, or who put them there, or how long they've been there. We don't have those initial conditions. That means we don't have data for the entire length of that particular experiment. That means that these are historical questions. This type of science is called historical science. These are less scientific because you just have less data, technically speaking. And at least in my opinion, meteorology falls within this category, which is why the weather person is always wrong. Because you're trying to predict things that you can't possibly know, trying to use data about the past you don't have. So, operational versus historical science, it is worth knowing the difference between those two things. It is technically over halfway through the lecture, so I'm going to take a minute to rest my vocal cords for a moment. Everyone can get some water, go to the bathroom, etc. And when we resume, we will make sure everyone remembers metric prefixes. And then we will move on to what we get. Anyone need anything or have any questions before we continue? Okay. So, in most academic science that you could possibly do in your lives, most of those disciplines are going to be using a metric system for their measurements. If you were raised here in the United States, then you're probably used to the imperial system, which has nice fun units like feet and pounds and gallons and miles in it, which sadly have a bunch of weird conversion factors between all of them, which I can never remember. Neither can most people. So we use the metric system because all of the conversions between different size units are base 10. Has anyone not used the metric system before? Okay, good. So this should just be review. The base metric units are, at least like the three famous ones that were invented for the metric system, are meters for length, liters for volume, and grams for mass. Weirdly, the United States doesn't really have an imperial unit of mass. Instead, we just use pounds for weight and use that as the only measurement of how much matter is within an object, even though it's not a very accurate reading. And from there, we can scale things up and down using the prefixes. I keep having to remind myself that hecta exists, but this set of conversions all goes in scales up and down in factors of 10. Base 10 times smaller is deci, then another 10 times smaller is centi, another 10 times smaller is milli. For base, 10 times bigger is deca, 10 times bigger is hecta, and then 10 times bigger is kilo. Of those 6, kilo, centi, and milli are going to show up the most, but there are a few bigger than kilo and smaller than milli that will show up from time to time. But scientists got sick of naming every step of 10 and then just decided to do it in steps of 1,000. So a megameter is 1,000 times bigger than a kilometer, and a gigameter is 1,000 times bigger than a megameter. I will remind you guys as those come up. Smaller than milli though, 1,000 times smaller is micro, 1,000 times smaller is nano, so on and so forth. I believe 1 attosecond is the smallest unit of time that we've measured. I still don't actually know how, but I have been told that fact. And there's going to be a lot of converting back and forth between different metric prefixes. So, very briefly, 3 very quick metric conversion questions. 1, how many kilometers is 10 meters? Now, whoops. The reason that I put this on the board, and I'm frequently going to do it, is some people, including myself, are tactile learners, or at the very least visual learners, and it behooves some people to have something like this to do what I call the skip hop method of conversion, where you take your base unit and you literally jump towards your last unit. So this is something that I'm going to do on the board from time to time, and it helps me make sure that I'm converting up or down in the correct direction. Because it's easy to remember that kilo and base are a factor of 1,000 apart, but some people, including myself, frequently make the mistake of multiplying where one should divide it, and vice versa. So I put this up sometimes just to help avoid that question. So if we start at base meters, I will jump 1, 2, 3 places to the left, and that's going to give us 0.010 kilometers. I am in the habit of adding a 0 in front of my decimal points. Some scientists appreciate this because it makes the decimal point easier to see, and it makes it more obvious that it's not just a period from a previous sentence. It is not required of you if you're answering a question and this is the answer and you leave it that way. It's fine. I'm just letting you know I do this, and that's why that 0 is there. So how many kilograms is 100 centigrams? Will the answer be bigger or smaller? Smaller. So 1, 2, 3, 4, 5 places over. I believe that is 0.001 kilogram. Zoom tight, whoever sneezed. And 1,000 kiloliters into milliliters. 1, 2, 3, 4, 5. 6 extra zeros tacked on. So that's going to be a billion. We're going to be doing these constantly, which is why I have to acknowledge them at the front of the class. Sorry, the beginning of the class. So, foundational stuff, we have to acknowledge it, but I trust this is something you've been doing for a while. But if you haven't, and if any questions pop up, do please ask them at absolutely any time. Now, converting between different scales of prefixes isn't the only type of conversion we're going to do. There's also converting between different measures of the same thing, or different units entirely, rather. And I mostly want to just do these two quickly with you guys to show you the way that I convert. Because I have in the past, without having explained my conversion method, just started doing it up on the board, and it confuses people visually. So this is mostly me explaining why I do what I do. You don't have to do the same thing, I just want to make sure it makes sense. So, first question, how many seconds are in one day? I employ what I was taught, I was told this was called the railroad method. It kind of resembles railroad tracks. Start with a measure of 1 day. I want to turn it into seconds. So I set up, and it kind of looks like railroad tracks, although probably more like fence posts. I know that there's 24 hours in 1 day. So I fill that into the next set of railroad ties. And this is functionally just multiplying by 1 in a very weird way. What I mean by that is, the conversion 24 hours equals 1 day. These two things equal each other. They are the same value, just a different unit. I can send 1 day to the bottom of the other side. That creates a fraction that is equal to 1. I divided both sides by 1 day. 1 day over 1 day would be 1. So this fraction equals 1, which means every single part of this railroad network is just multiplying by 1, but in a way that's going to cancel out the old units and replace them with new ones. So that's why I use this tactic. Days go away, so 1 times 24 would be the hours in a day, but we already knew that one. So 1 hour is 60 minutes, and 1 minute is 60 seconds. My handwriting is deplorable, and I apologize for that several times as the year goes on.